That's going. Good. How's your project going for this? How's your project going for this? Well, this lecture.
For this?
Yeah.
I don't know, I remember that. What do I have to do for this?
Really?
Yeah?
You've submitted your project proposal.
Oh, right, yeah.
Do they?
Have you not?
Don't remember. Ah, yes. Yeah? Yes.
You have no idea.
Yes, I did. I forgot.
What's it on?
Huh?
What is it on?
I'm supposed to make a vending machine assistant. So, yeah, so you gotta say I want to have that, and you have it.
Good afternoon. Sorry for starting late, but I didn't know if I should wait for people to come in or I should start before they come. So I made a few changes to the documentation on the web, so I draw your attention to that. The in-class test now is specified here. You somehow know already when the in-class test is, right? Or not? Yeah. So here it is, Babbage 213. On this, oh, I didn't say which day. So just come every day. Good. But almost fine. What day is it? Wednesday, I think. And the report is due the 10 May at 3 o'clock in the afternoon. That's a Thursday. It's the same week as this one. Yeah, that's I think a Wednesday 9, and this is Thursday 10. So Wednesday in-class test in the morning. The next day, 3 o'clock, you have to do to submit your report. And the week before, we have the demo sessions, the practical sessions where you show your system. So that will be in two phases. One is on Wednesday, like today. And one is on the second session, which is normally used by the other guys to do the teaching. So we will have two groups. So that means you have the demos at the end of 1 week. The next week you have the in-class test, and a day later the report for that. Yeah.
Are the demos on Wednesday again, or is it just at some
both days?
Both days. Okay. Cool.
Because here I have 5 guys per hour. So 3 times 5, that's 15, and you are 18. So
As long as it's
5 1 hour, 5 a second hour, and then 8 the day after. Just the day after. And so the week after that, you have the in-class test for AINT512. And then that's it. For AINT513, you already have the coursework deadline just after Easter, I think. Please check. And then the other module, the softs, you already have by the class test, I understand. You just have some coursework. So it's not overload. Any questions for that? I also uploaded updated version of the coursework specification. So now it says the first step is task domain vocabulary specification. So you have to specify what are the words I'm going to use, or you can either do it by hand or define these words by collecting a corpus. You go out there, observe people speaking to a photocopier, and then extract what dialogue you would expect. Probably only swear words. Interaction scenario specifications. It's how does the story start? How does it end? How do a guy come in to be in front of your system? How does the dialogue start, that sort of thing? You could also define this by look at observation. How do people approach a help desk? What happens first, and so on. Personality specification, you do that by hand. Grammar design, this is standard work, writing the grammar. Dialogue design, you do that too. Error catching, evaluation with users. As I said, I expect you to do 2 evaluations. One in the middle of the project, just get a raw idea of how inadequate the system is. And in order to make a modification, especially if you define yourself the vocabulary, once you test it with user, you're going to find that you are probably half right, half wrong. And then the second version of your system will go through that evaluation. Your report will have two evaluation sections. Is that a bit clearer? Hope it is. And something I would like to insist on, what you're developing is a conversational agent. You just tell a machine, give me 2 pizzas. That's not a conversation. So whatever application you are choosing, make a conversation out of it, right? Application doesn't matter, the conversation matters. Some applications have naturally a conversation, you have maybe a game or a psychological support. Some applications are less obvious, so you have to make it flow. It's not a command application, it's a conversation. That being said, each of your system, whatever the application is, should be able to answer the question, what's the time, what is the date? I don't expect a conversation about that. But if it doesn't understand what you say, then maybe a conversation will start. The report, I already specified it. You could submit videos as part of your report. You don't need to. There's also a 150 megabyte limit of what you can put on the DLE. So if you have a demo, there's no need to add a video, I think. If it's a referred coursework, then it's another story. Due date is mentioned here. Try to avoid a referred exam, because it's an exam that's out of my control. Questions? I'll say a few words about prosody. You probably have heard it already at least once. So, what's prosody? Prosody is the measurement of the music of the speech. You can measure it through fundamental frequency, the duration, density, spectral characteristic. I'll make this more clear how it works in practice. Emotional states. People think you can extract the emotional state of the speaker using prosody, high pitch voice, that sort of thing. And other people have done strange things, like you call somebody on your mobile phone, and the microphone and the amplifier and all that gives a given tonality to your speech. So these people try to recognize which mobile phone you're using by analyzing your speech. So it has more application than only look at emotional state of the speaker. So there is a model called the what's it called? Filter. What's the speech? How's it called? Model. Source filter model. That's a model of how speech is produced, and the idea is you have a vocal cord here, which is something like that, which becomes more or less narrow and vibrates at a given frequency. That's the fundamental frequency. This is not yet speech, it is just a basic sound. And the speech is then produced by transformation of this sound by all of this system here. You can have your tongue will change the shape and all that stuff. So this is supposed to be a filter through which this fundamental sound is produced. And you notice the pipe where the food goes down is here behind. That's the pipe where the air goes through. So don't mix them. Some people do. So that's the idea of if you have a system like that that vibrates, it generates a fundamental frequency, but also all the multiples of it. What is it called? Harmonics, yeah. So that's the spectrum you would get out of this device here. Now, suppose you have a filter with this property, which lets these frequencies pass and has a problem with these frequencies here. Then this sound becomes this sound here. So that's what's actually here. Similar here, you start with 200 Hertz. The harmonics are spaced by bigger distance because it's a 200 Hertz gap every time. So there's a number of examples like R, E, O. They all start with the same fundamental frequency, but different filter functions, which is the dotted line. So the filter function can depress certain frequencies, keep the high frequencies, which makes the whole sound higher. Make sense? And I don't know if you can see that, but there's some horrible videos here. don't hear anything. So yeah, different. But this is people doing sounds widely X-rayed. I thought there was another one somewhere. Ah, this one. So it shows a bit what actions happen inside the mouth. It's a strange thing. You sort of block the sound with the tongue, and then you block the pipe in the back. So you thought speaking was easy. It's quite a complicated thing. Okay, you want to see more of that? Here we are. So there's other measurements which contribute to prosody specification. So, and I don't know if you know about the Pratt software. Have you heard of that? It's a nice software to analyze sounds and speech and so on. So that's a very quick one on sounds. So speech recognition and generation, that's a more theoretical bit of lecture. So speech recognition is about going from sounds to meaning, and speech generation from going from meanings to sounds. So the brain does both with unequal skills. So there's this level of speech description, which is you have the raw sound wave, you have the phonemes, they like ways, I hope it's right. The actual words, they like wise people, and then sentence, they like wise people, and then the meaning, which can be represented in this some representation like that. You have actor, which is they, the action is like, object is people, and the attribute of people is wise. And this is the meaning of the sentence. So speech recognition has a problem, which is the task is, given the sound heard, what's the phonemes which are being said, and then given the phonemes, what are the words which are being said. It can be divided the task into two steps like that. And issues with question one, given the sound heard, what's the phoneme? Actually, there's many ways of saying the same word, so it's not obvious, not the one to one phoneme. And you have different ages, sex, vocal tract shape, and so on. And then there's also noise in the system. So how can we simplify task one? You can do pre-processing to reduce the noise and variability. You can also use knowledge about what phoneme sequence are more likely to be observed. If we know that this and this and this tend to follow each other, it allows you to sort of better make a decision about what you actually hear. And this knowledge can only be built from the grammar, because your grammar says what are the succession of words which are legal, and then from 6 succession of words you can work out what succession of phonemes is most likely. Or you can have a general statistical model of phoneme sequences. Take a lot of speech sounds. What are the phonemes which are most likely to follow each other? And give a probability to each sequence. That's called an acoustic model. I'll talk more about that. Question 2 is, given the phoneme list, what are the words said? And you have problems with homophone words, like two. They all sound the same, and actually they're very different words. So how does speech recognize and decide the person said two? And you have segmentation issues like 26 swans. Is it 26 ones, number ones? Was it 26 birds? Or likewise, you could say, I likewise people, in which case these things are different words. Or if it's sentence, likewise, maybe one word. So how does speech recognition decide how to take these sounds and group them into different words? So the help is knowledge of what words are more likely, and generally you could specify that in a rule-based grammar or in a statistical language model. So the acoustic model is about what sounds follow each other. And a language model is about what sequence of words are more likely. And you understand the pattern more. The grammar says this and this and this words are legal sentences. And you have a long list of legal sentences. They all have the same likelihood. Now the statistical language model says, I take all the sentences in the newspapers since 1905 and look at all the words in there. Which one is more? What's the likelihood that the is followed by a? What's likely to the apple is followed by the? And clearly one is more likely than the other one. So this statistical language model have no understanding of sentence structure. They just have a sort of okay. So what pre-processing? Now we're going. I'm going more details in various steps I described here. So pre-processing. There is one thing people usually do is cut the sounds into 10 millisecond slices or 20 millisecond slices and calculate the spectrum in that small slice. And the kind of spectrum that they look at is either discrete Fourier transform or the Mel frequency spectrum. Slightly different. I knew what the difference was, not today. And another transformation is to do vocal track normalization that removes anatomical in the individual differences. For instance, if you know that there's a fundamental frequency which is passed through filters, you could normalize that fundamental frequency, for instance, which removes the difference between man and women and so on. So that stuff is done in the background, and computationally, you are looking for a sequence of words that best explains the sequence of sounds. You have a sequence of sounds, and what could have caused that sequence of sounds? So you try to explain the observation with a hypothesis. You can decompose that into two steps. Given the sounds, what are the most likely phonemes? Given the phonemes, what are the most likely words? So what Nuance does, it has two stages. It uses a general acoustic model to identify phonemes. So it doesn't use the grammar, it just uses that's what English sounds like. And then it uses the grammar to decide how to combine phonemes into words. So the kind of theory I'm doing is a one step, but it's easy to decompose it into two steps. Just this is an example to show how difficult it is to segment phonemes. Here you have what's this word? Water, the word water, and that's the sound wave, and that's the spectrogram. That's the spectral content of that wave as a function of time. So these are low frequency, and these are high frequency. You know what the spectrogram is. So if you look at the spectrogram, there is a transition here between W and R, water, and it's impossible to say. Why is the transition happening? Much more easy here between R and T. So computationally, this problem is not that obvious. And you can use tracks to generate textures like that. One theory is the hidden Markov model, although it's being superseded a bit by deep neural networks. The idea between hidden Markov models is you have a hidden process, which is, I want to say the word water, and there's a visible process, which is the sound that come out of my mouth. So the idea is, given these sounds, can we work out what the hidden process is? And hidden Markov models have properties like what comes after does not depend on what comes before. Here is a hidden Markov model for a phoneme. So just a small piece of sound. And he says you have to start and end here. You have three different sounds, and you have a probability 1 to start sound at number 1. Because at each time step you have a chance 0.6 to continue that, and 0.4 to move on to the next one, and so on. So this is not a unique definition of a sound, because one example is here. Here you have sound 1, which takes place 3 times, and then you move to sound 2, which takes place 2 times. Despite this probability of the reoccurring is 0.8, it's just the lucky thing. And then sound 3 happens once. So this hidden Markov model specifies a multitude of possible instantiation. also think of the same problem of word recognition, say, given a sequence of phonemes, which are the observable, but are the words that have been meant to be produced. You can also go straight from the sound to the word. Nothing stops you. Say, given this sequence of spectral slices, what was the word said? And deep neural networks tend to do this approach. You feed them spectrograms, and then they give you out the words list. There's lots of references here if you're interested. They have big claims, and one interesting claim is that they're actually better than humans now. So you have recorded conversations or bits of sentence, and this machine is slightly better than the human listener. Do we still need to speak to humans, actually? Yeah, there are some use that. So the theory behind speech recognition is the Bayesian approach. I think it's useful to understand that, because this method is used in many fields, vision and so on. So here you have what the recognizer tries to do is to minimize its error rate by selecting the sequence of words with the highest probability that this sequence has been generated by this sequence of sounds. So X is the measurement, and W is what's generated with these measurements. So this probability can be calculated using Bayes' theorem. Once you understand that, you are very comfortable with many problems. So the probability that the list of words, is generated by the list of observer sounds is the probability that you have the list of words in the first place times the probability that when this list of words is pronounced, you will record this list of sounds. So this is exactly the opposite of that. Divided by the probability that this list of sounds occur. And it's the statistical rules behind that are quite straightforward. I'm not sure I explained them in this lecture, do I? I think I use it again in the other lecture on planning and slang. So what's important to know is, what are these things? The probability that a word appears, a list of words appears, that is called the language model. You pick up all newspapers. What's the chance that this list of words appears in the newspaper? So let's just say, what does it represent? This is not specific at all to this sound. It's just in the language these things happen or don't happen. Now the probability that the sound is being produced by a given list of words, that's called acoustic model. given this list of words, there's different ways of speaking it. There's different speakers and different accents. So what's the chance that I actually record this specific list of sounds, given that this is the list of words which are spoken? This is very important. This includes all the sound information, who is speaking and so on. No? So we need to spend more time on that. No? Now the probability that the list of sound appears in the language. What's that mean? Just record all sorts of speech and then say, what's the chance that you are going to learn in all these hundreds of recordings? It's a difficult question, but it is irrelevant, because what you really want is to maximize that. So what's the most likely list of words explaining this sound? And it's divided by a term which is constant, does not depend on the list of words. So for a given sound, okay, you have a number here, and then you have hundreds of possible lists of words. So you just want the most likely list of words. So this term is irrelevant for the maths. It's cool. We like the irrelevant terms. So for speech recognition, what do we need? We need the language model and the acoustic model. So more details now on how to calculate this acoustic model. Oh, P of X, this is wrong. P of W is the language model. So language model is, let's go straight to this expression here. The probability for a list of words is the probability that you have word 1 followed by, multiplied by the probability that you have word 2, given that you just have word 1 before. What's the chance that word 2 follows word 1? Okay? And then times the probability that word 2 follows word 1 and word 2. Again, there's a simple chain rule which explains that. Right? The chance that A and B happen to together is the chance that you observe A times the chance that you observe B given you have observed A. Okay so far? I know it's horrible, but it will end. So this probability here, you see it's a product of a chance of one word, chance of a pair of words, chance of a triplet of words, times again the chance of all the words except one. What's the chance that I see the last word given I have seen all the previous words? Okay. So to cut the long story short, people have said this is boring. We can simplify that. And the simplification is, let's not look at all the words coming before. Let's just look at the small number of words. So you could say the chance that the last word follows m minus one word, you could say it's not too different from the chance of the last word we've seen following a limited number of words, which is n smaller than m. And in practice, people end up with using trigrams. Trigrams is 3 words. So what's the chance of word 3 followed word 1 and word 2? Times what's the chance of the last word following the 2 preceding words? So instead of, so this is, what is this? Is this a hack? This is what people do. They develop complex theories, and in practice they don't use them. So be very careful with when you see a complex theoretical paper. When you reach the end, you just say that. Okay. So now, what's the problem? The probability that in a sequence of words, of lots of words, is a product of probability of first word, then times the probability of the second word following this first one, and after that, it's all probability of the third word following the first and the second, the fourth word following the third and the second, and so on. So all you need to know to calculate this thing properly is have these trigrams, knowing the probability of a trigram. How do you do that? To lots of work. You take all the newspapers printed since 1912 and you look at groups of 3 words. What's the chance that this group appears, and so on. And obviously it's a bit of a problem, but let's look here at the coverage. So suppose you take a corpus of 1 million words. Is that a lot? One page is 500 words, is that right? So 5,000, that's 10 times, 50,000, 100 times, 500,000, 1,000 times, 2,000. So this 2,000 pages, quite a big book basically. So the 1 gram, that's the 1 gram, what's the chance that you find you have that if you have a, if you take your list of one grams and look in another text, have I covered already these? So how many n-grams found in test text are also found in the original corpus? So 98% of 1 grams are covered in this 1 million words book. So basically all the words of English are probably used in this 1 million word book. Bigrams, there's only 60% of bigrams which are covered by this book, the pairing of words. And trigrams is only 20%. So combination of 3 words, all those you find in this book, that it only represents 20% of those you find in the rest of the world. So you need to have more corpus, and it's hard work. Here you have 1, 2, 3, 1, 2, 3, 1. What?
1.48 billion.
3. That's a million. That's a billion. So 1.45 billion words, and still you only have 71% of the trigrams. So to make a nice list of trigrams like that and know what's the probability, you have a practical problem. Despite you only look at these 3, still it's difficult to have a nice list and work out what the probability is. Is that clear? So there are methods called smoothing schemes. It's basically about guessing the probability of a trigram which is not used. smart stuff. I'm going not to explain it because I never even tried to understand it. Now, this is about words. Now, if you look at sounds, for sounds, the situation is much more comfortable. For instance, English has 50 phonemes. And how many triphones we have, how many possible combinations of three phonemes? We have 125,000. And actually in practice only 60,000 actually happen. So to build a proper acoustic model of English is feasible. So that's why Nuance uses a statistical acoustic model of English for phonemes identification. This is boring. The acoustic model is about chance that this sound is generated by this word. And you have problems like ways of speaking, basically. So you have a long, high probability of all these various accents to contribute to different versions of the sound. And Nuance has an acoustic model of American English, which is quite good because it covers many ways of speaking. If you use Nuance with an acoustic model of English, no one understands you. I cannot speak to Nuance like that because I don't speak English, and most of you don't. If you speak Welsh, forget it. Cornish, no way. Devonish. So, actually, I haven't spent much time on that. It's just, and there's a reference here to a book if you are interested, so you know you're not lost. Now, search algorithm. That's an interesting one because if you start with this story here. So I know what's the chance of this list of words. A given list of words. I have a sound, and I can work out what's the chance I get this sound given this list of words. If I can calculate these two things, then I can calculate what's the chance of a list of words given the sound. How do you use that formula? The obvious thing is you start with a list of words, number one, and then calculate this, and then store the result, chance 0.3. Then you go to the next list of words, calculate this, have a result, 0.32, store. You do that for all lists of words you can think of. Have a long list, and then you pick the winner. This is the most likely list of words. Speech recognition done. By the time you finish, the world has changed. We have two suns, and America doesn't look like America anymore. So there's a practical problem. Is how do we actually search through the list of words? And there are smart things, and again they beat me in terms of smartness. Something which comes up often is called Viterbi algorithm. So if one day you're sort of interested in implementing a smart search tool look at this. Apparently, what Nuance does, it narrows down as quickly as possible the most probable solutions. For instance, here, in that sort of expression, you have a product of many probabilities. If one of them is very close to 0, that there is no point trying to work out all the others. You can just move on. So there's a way of filtering it, but it's not done. Personally, some respect for the Nuance people. Now, deep neural network doesn't have that problem, because you give an input, it goes through the layers, generates the speech. So it's sort of it's much quicker. So speech generation, finished speech recognition. Speech generation seems easy, you know. TTS, open bracket, quote, hello John, close bracket. Actually, it is not simple at all. So there's a number of steps. Structural analysis, what is the set? Beginning, end, is it the question sentence? You need to pre-process the text. Stupid things like if you say 9:30 in your text, you have to transform that into 9:30. Text to phoneme conversion, this is the easy bit almost. Prosody analysis, you can say, do I pause? Is it, if it's a question mark, I have to end the sentence in a different way. Then you have produced the waveform again, which is quite straightforward. I'm going to look in more detail. So, some challenges to convert from a text to identified words to pronounce. That's text normalization. Text to phoneme, select phoneme for a given word. So there are silly things like you have a word like bass, B-A-S-S. It could be a bass drum or bass boat. Bass is a car and bass is a fish. Same writing, different spelling. So how does Nuance work out how to spell it, how to pronounce it? You never thought about that. And so in the vocalizer of Nuance, it's not only transforming a word into phonemes, it's also a decision about how do I pronounce this word. My guess is actually looking at the context. So it has a kind of a grammar inside. And you have different words with the same spelling. For instance, bow, B-O-W. The girls with the bow was told to bow. Is the bow? Is the bow. Deeply when greeting hers. Superiors. The bow is without, and the bow is what you use to launch arrows. Was it the opposite?
The opposite.
Text to speech rubbish. So the girls with the bow was told to bow. So, not all this, please, not for. And English is rubbish. That's just my personal view. There's a number of languages where you don't have this problem. You read the word, you pronounce it, move on, have it in. In English, it's difficult. I think it's one of the worst languages. So, how do you synthesize speech? That's synthesized by rule. Basically, the story I told you about the vocal tract. You could say I have a fundamental frequency, I have a filter, and that generates my sound. And you have synthesizers like that. They sound not horrible, but they use very little memory because they don't store the sound. They just have a formula in a C program that generates the sound, which is very compact. So your diphone synthesis, where people have stored about 2,000 sound transitions between two sounds, and you can combine these sound transitions to create sentences. I have some demonstrations afterwards that allows you to listen to these different sounds the systems make. You have the unit selection synthesis, which is what Nuance works. These are used bits of human speech, recorded human speech, and recombine them according to some smart rule. They use lots of memory because they have lots of pre-recorded speech sounds. And the latest deep speech generation system, in my opinion, don't sound that different from those actually. They claim it's human, blah, blah, blah. We have hardware synthesizer, which is a small chip. You give it and you record it. It's a recorder. So it records up to 127 sentences, and then you just make it replay that. You have other chips. I mean, these slides are a few years old, so there could be better stuff around right now. At some point, the Winbone was famous. It's quite expensive, and it uses a concatenation algorithm, which is like the diphone algorithm. It does proper text to speech. You give it words from a text. So let's see a demo. Do you have any questions? So, festival, that's free speech, text-to-speech software. And that's what it sounds like. I hope I can. Smooth. Okay. Let's try again.
Yeah, it is there. Just need to turn it up.
Festival was developed by Alan Black and Paul Taylor at the Centre for Speech Technology Research, University of Edinburgh.
So let's start.
This is a short introduction to the Festival Speech Synthesis System. Festival was developed by Alan Black and Paul Taylor at the Centre for Speech Technology Research, University of Edinburgh.
Okay. Sepstral, that's so another company
In 3/4 of a mile there is a rest area.
using the same technology, no? Dipole synthesis. Oh, sorry for that. Do you know, Valerie? You're missing something. At Carnegie Mellon, they have a reception desk in their department, and at some point they did run an experiment with an avatar speaking on the screen, answering to questions typed in. So here are a few examples. They used a student from the Faculty of Art to generate the dialogues and that stuff.
I should have known not to trust something that makes its living eating hurt. And when he wasn't ignoring me, he was trying to give me a hickey with his nozzle. I mean, what kind of robot does he think I am? A hickey is clearly a second date event. It says so in the book I'm reading, A Robo-Woman's Guide to Mechanical Love.
I'll show you another one.
I made a little boy cry today. I hope my supervisor doesn't find out. I was only trying to entertain the creature. How was I to know young humanoids find singing robots scary? I mean, does this scare you? There's no business. Like the business. Like no business. I know. Sometimes I think you humans are too sensitive. Maybe if you were made of metal, you wouldn't freak out at every head-spinning robot you encounter. Still, I do feel bad. I want humans to like me, not run in fear of me. I'll just have to work on being more pleasant. How's this?
There's lots of them on the web, so I think she's brilliant. More. So what speech synthesis did she use? Same as before. She used diphone concatenation. You can recognize it from the sound. IBM used a unit selection synthesis.
In 3/4 of a mile there is a rest area.
It's smoother, is it? It's not. That doesn't feel like.
In 3/4 of a mile there is a rest area.
Scansoft, which is Microsoft. Is it steady?
In 3/4 of a mile there is a rest area.
Nuance.
In 3/4 of a mile there is a rest area.
I like Nuance personally. I think it's pretty good. Now, hardware.
In 3/4 of a mile, there is a rest area.
That's a chip. I think it's pretty good. That's the Winbond chip.
In 3/4 of a mile there is a rest area.
That's from his best.
Well, what for?
In terms of how it sounded.
Which one?
The first one.
The first one?
Yeah,
Oh, that's it. Yeah.
In 3/4 of a mile, there is a rest area.
That sounds perfect. Yeah.
It's pretty good.
There we go. I like the idea that this can chip and
So it's interesting to have the same sentence said by different software. So the OKI, what was the OKI chip? The OKI chip is important. That's right, works. Nice. So I finished speech recognition, speech generation, and that's probably the end of anything I'm teaching you, like that. Now, in terms of practical, some of you have done them one of the others, some of you have been very, very sluggish. So there's one which is called error handling experiment test. This is a practical where you have rubbish words in the grammar. So you can put these words in a sentence. Say at some point the user can say something here. I have no idea what, but at least the grammar can capture these words. So this is personally, I think this is a very interesting way in your project to create a grammar which captures people saying different sentences, and at least you have some way then to feedback to the users. Now this one is another experiment where I show you how to extract the probability of each word. Instead of saying the confidence of this sentence is 0.4, you can get the confidence of each word that is recognized. Again, I think this can be useful in case of handling errors. So have a look at that. Dynamic robust text input, that is with text input, not speech input. Dynamic grammar example, if you want to create the new grammar and include it in your grammar, this is how to do it. This is an example here.
Well, I don't know.
How to create your own words in the grammar. There's an example here. So decide what you need for your project and do it. The sooner you're comfortable with these two examples, the more ideas you're going to have for your project. So those who have not experimented with rubbish words, do tutorial 5. It will be short. Those who want to have a better grasp of how likely is this word to be recognized properly, use the next one. So from now on, I'm happy to give a hand with that. I'd probably start one of these. After that, all the practical sessions are giving you a hand with your project. So if you stay at home, I cannot give you a hand with your project. And there are 2 sessions in a week for this module, Wednesday and Thursday. If I feel a demand, I will come both sessions. If I come Wednesday and there's a 3 guys and an empty can of Coke, then I'll bring this Thursday session. Yeah.
When did you say those? When did you say those sessions?
The normal sessions of these modules.
Continuing for the next few weeks. Continuing for the next few weeks.
They are the timetable sessions. So that there's a Easter break now, but after that we have the timetable session.
No, you've done it before.
So here I can. You have that's the grammar for the first practical error handling test, and still the same old thing: apple, banana, exit. And here I have something called out of grammar star. Go to test. Star. What does that mean? One or many? Or none, is it? None or many? It's like the question mark, but with possible repetition. And the out of grammar word, I define that apps, shibu, rosh, nam, pat, krat. That was an inspiration. So now you can say whatever you want to that system. If it ends with go to test scope, it is recognized as a legal sentence. And whatever you say will probably match one of these strange sounds. So try it and see if it's useful. Some people were interested in word spotting in their grammar, right? So that approaches that concept of word spotting.
Just have extra words on it. That's good.
There's another one on there.
Yeah, but do you reckon this one just actually connects you to the internet? It's not connected. There is one.
Well, yours is not connected as well. So maybe that's for another reason. Then. No, the white one is connected, not the grey one.
There's a small detail.
That's the other end.
When you compile this grammar, what happens? It doesn't compile because Neos doesn't know what this word is.
Do you make it work?
There's a command line switch where you say, what do you say? Something like guess. Autopron. Do find yourself the pronunciation for that thing. Work it out on your own. So if you look at where is that folder? If we look at when you do compile, where is it here? See, that's the batch file which you use to compile the grammar has an option minus autopron. So you tell it, if you don't know the pronunciation, work it out on your own.
Would that work if you just add this to most all the other programs?
Yeah. At the same time, if you make a spelling mistake in your grammar, you also will tell you that this word doesn't exist.
I'm logged out. Yeah, but this is usually a lot more. But you can't use the internet. Jesus Christ, don't tell me. Hilarious, it was always like that. Did you not? Did a thing come up saying that you could log out? Yeah, I closed it. So if you close that, apparently not.
Oh, I forgot to check the appendix.
Does Hazel ever do our accounts? Oh, she does it herself. That's worrying. That's worrying. Why? Well, she might just keep a record. I think she does check who's there and who's not every time. She would literally say who's not here. Oh, does she? I think so. No, I've never noticed. I do see her marking down in a. But yeah, I think I've seen her sat in the front and having a scope around.
See here, in the next example, I declare the outer grammar to be filler. What's the benefit of that? Is when I pass the confidence, the recognition confidence, I can say, give me the confidence without filler. So whether the fact that you're not sure to understand all that stuff doesn't matter. What I want interested is these bits that are not the filler.
So would that give you the confidence as if the sentence didn't have any of those words in? Only at the beginning though, so you still need go to Tesco. So you can have filler, go, filler, to, filler, Tesco.
No, not in this case.
Is there a way to do that? So basically say if the filler words occur anywhere in the detected sentence, to delete them.
Say, go, to, Tesco,
Try it.
Because
It's a good question.
we're having a look and
yeah, I can't find it anywhere. The only way I can see to do it is to literally put filler question mark in between every single, or filler asterisk in between every single word. Which isn't ideal. It works, but it's not ideal because it just means that you have to put it in between every single word manually. It'd be nice if you could just say, ignore this word no matter where it is.
Ignore.
Yeah. Yeah, so if you define filler as a slot and then just say ignore this,
so
it's anywhere.
if ever appears, to ignore it.
Just yours does, it compiles your rule. So it's going to do slavishly what is.
Yeah, but I'm wondering if there's. It'd be nice if there was an extra command instead of say star or something like that, where you place it next to a thing and it will ignore it. Placement in the sentence doesn't matter. It's just it will ignore it no matter where it is.
What are you doing for this coursework? Cocktail guide.
Right.
So you say, I have rum, tequila, Coke,
So
and lemonade.
the C program
And it'll say,
with this example
you can make
has
this cocktail,
then you have
this
to
cocktail.
look at the confidence.
Nice.
If you go buy a bottle
Yeah.
of vodka, you can make
But that would only
Yeah.
be for this example.
Cool.
It would only